There exists a moment in human history when we finally looked far enough back into the cosmos that we could see ourselves as we truly are. Not as the center of creation, not as the pinnacle of existence, but as a fleeting arrangement of stardust that has somehow awakened to contemplate its own origins. This moment arrived quietly, without fanfare or trumpet calls, when a space telescope named James Webb, positioned 1,000,000 miles from home, shielded by a golden parasol the size of a tennis court, opened its eyes to the universe and began whispering secrets that would forever alter our understanding of existence itself. To understand what happened when James Webb looked too deep into space, we must first understand what it means to look at all. When you gaze up at the night sky, you are not seeing the present. You are witnessing the past, ancient light that has traveled across incomprehensible distances to reach your retina. A photon of light from the nearest star system takes over 4 years to complete its journey. We see Proxima Centauri not as it is now, but as it was when your grandparents were children. When we look at the Andromeda Galaxy, we are seeing it as it was 2.5 million years ago, when our ancestors first began walking upright on the African savanna. The deeper we look into space, the further back in time we travel. And when James Webb finally turned its instruments toward the deepest darkness between the stars, it didn't simply observe distant galaxies. It traveled back to the very dawn of cosmic history, to a time so remote that the universe itself was scarcely older than a human civilization. For nearly 400 years, humanity had been building increasingly sophisticated telescopes. From Galileo's crude optical tubes that first revealed the moons of Jupiter, to the massive mirror arrays that peer into the electromagnetic spectrum from mountaintops on Earth, we had slowly extended our vision into the cosmos. But there was a fundamental limitation that even the most powerful terrestrial observatories could not overcome. The Earth's atmosphere, that thin veil of gases that makes life possible, also acts as a barrier to certain wavelengths of light. Water vapor, dust, and the warmth of the planet itself created distortions and absorbed crucial information that was traveling to us from the distant universe. The atmosphere twists and refracts starlight, creating the twinkling that appears so romantic to the naked eye but proves so frustrating to the astronomer seeking precise measurements. In the 1980s and 1990s, the Hubble Space Telescope changed everything. By placing an observatory above the atmosphere, humanity finally had an unobstructed view of the cosmos. The images that Hubble sent back were breathtaking. They showed us galaxies beyond counting, stars being born in vast nebulae of gas and dust, supernovae exploding in distant realms of space. When astronomers pointed Hubble at what appeared to be an empty patch of sky, no larger than a grain of sand held at arm's length, they discovered thousands upon thousands of galaxies, each containing hundreds of billions of stars. The deep field image that resulted from this observation became one of the most profoundly moving images ever captured by humans. It forced us to confront the sheer scale of the cosmos and our infinitesimal place within it. That image transformed our understanding of the universe's scale and complexity. Yet even Hubble could not see far enough back. It could detect light across a range of wavelengths, but there was a particular frontier that remained largely inaccessible. In the early universe, when galaxies were first forming in the aftermath of the Big Bang, those galaxies were so distant and so ancient that their light had been stretched by the expansion of the universe itself. This stretching, called redshift, shifted the light from the ultraviolet and visible wavelengths that Hubble could see into the infrared, wavelengths that require specialized detection and are nearly invisible to conventional telescopes. To see the first galaxies, to witness the actual moment when the universe transformed from an era of darkness into an era of light, we would need a new kind of observatory. we would need to see an infrared. We would need the James Webb Space Telescope, an instrument that represented the pinnacle of human engineering and scientific ambition. The James Webb was named after a former administrator of NASA, though the name itself carries less significance than the vision it represented. Here was an instrument conceived in the 1980s as a response to a question that had haunted astronomers since the earliest days of modern cosmology. When did the first stars ignite? When did the first galaxies coalesce from the primordial gas that filled the early universe? How did the universe transition from a nearly uniform sea of hydrogen and helium into the intricate cosmic what we see today, with its vast filaments of galaxies separated by enormous voids? These were not mere academic questions. They were profound inquiries into the nature of our cosmos and the processes that created the conditions for life itself. The construction of James Webb was not a simple undertaking. It represented the collaborative effort of thousands of engineers, scientists, and technicians across multiple continents. The United States, Europe, and Canada all contributed expertise, resources, and personnel. The engineering challenges were monumental. The telescope had to be designed to function in the harsh environment of space, where there is no atmosphere to protect instruments and where temperatures plummet to near absolute zero. The budget ballooned from initial estimates of around $500 million to nearly $10 billion by the time of its launch. Delays stretched across years and then decades. Skeptics questioned whether the mission would ever succeed, whether the engineering challenges could be overcome, whether the instruments would function as designed in the unforgiving environment of space. Technical issues, design revisions, and the sheer complexity of coordinating an international effort tested the patience of even the most dedicated advocates for the project. But the vision persisted. The belief that humanity could construct an instrument capable of seeing back to the universe's infancy, of witnessing light that had been traveling for over 13 billion years, drove the project forward through countless obstacles. Finally, on December 25, 2021, on Christmas Day, James Webb lifted off from the European spaceport in French Guiana. The launch itself was a moment of intense vulnerability. The telescope was so complex, so delicately constructed, that it had to be folded like origami to fit inside the cargo bay of an Ariane 5 rocket. Every mechanical movement during the launch, every vibration, every thermal shock carried the potential to damage something critical. As the rocket climbed toward the stars, thousands of people involved in the project held their breath. The countdown continued smoothly. The engines roared to life. The rocket accelerated through the atmosphere, shedding its protective fairing as it reached the upper reaches of Earth's domain. Throughout the ride, James Webb remained protected, folded and secured within the rocket's payload bay. In the weeks that followed, as the spacecraft traveled toward its destination at the second Lagrange point, a gravitational balance point between the Earth and Sun, hundreds of mechanisms had to deploy perfectly. Solar panels unfurled to catch the Sun's energy. The Sun shield, that golden parasol made of 5 layers of aluminized mylar, no thicker than human hair, had to spread and extend to its full dimensions. The shield was a marvel of engineering, designed to block the heat from the Sun and keep the telescope's infrared detectors at the frigid temperatures necessary for operation. The primary mirror, composed of 18 hexagonal segments made of beryllium coated with gold, had to align itself with submicron precision. Each of these segments had to position itself with an accuracy better than 1/1,000,000th of a meter. The secondary mirror had to extend outward and lock into position. The complex dance of deployment continued over the course of weeks, and each step had to succeed perfectly for the mission to proceed. Against all odds, Against the skepticism of doubters, it worked. Every deployment succeeded. Every mechanism functioned. By late January 2022, James Webb had arrived at its destination and begun its painstaking commissioning process. The instrument had to be cooled to a temperature of just 46 Kelvin, approximately minus 227 degrees Celsius, colder than the coldest naturally occurring temperature on Earth, colder than the coldest regions of Antarctica. The cosmic coldness of space, combined with the sun shield that reflected away the heat from the sun and Earth, allowed the temperature to drop to such extremes. The mirrors had to be aligned so precisely that if the primary mirror were the size of North America, the bumps on its surface would be no larger than a few inches. Specialized actuators, each capable of adjusting segment position by tiny amounts, had to be calibrated and optimized. The infrared detectors had to be fine-tuned to detect individual photons of light that had traveled through nearly the entire age of the universe to reach them. Then, in mid-July 2022, the first images were released, and the world paused to look at what James Webb had found. The anticipation that had built up over decades, the questions that had driven the project, the hopes of astronomers worldwide, all of these crystallized in that moment when the images appeared. The world saw what the deepest cosmic observations could reveal, and the result was awe-inspiring. The first target was a well-known cluster of galaxies called the Abell 370 cluster. But where previous observations had shown fuzzy, indistinct objects lost in the noise of background light, James Webb revealed structures of extraordinary detail and clarity. Galaxies that had appeared as mere blobs now showed spiral arms and dust lanes. Stars within those galaxies resolved into individual points of light. The sensitivity was so extraordinary that the telescope could detect light coming from distant objects that previous observatories couldn't see at all. Within the first few weeks of observations, astronomers had already discovered galaxies that were far more distant, and therefore far older than anything ever detected before. The universe, captured in unprecedented detail, revealed itself to be far richer and more complex than anticipated. But the true shock came from the deeper understanding of what these observations meant. As data accumulated, as the team of scientists analyzing the James Webb observations began to piece together a comprehensive picture of the early universe, a troubling discrepancy emerged. The galaxies they were seeing were too large. They were too mature. They were too numerous. According to our prevailing theories of cosmic evolution, it should have taken billions of years for galaxies to grow to the sizes and masses that James Webb was observing. Yet these galaxies existed when the universe was less than 1 billion years old. Some of the most shocking observations suggested galaxies so massive, so developed, that they violated the expectations of cosmic structure formation that astronomers had held for decades. The universe, it seemed, was more efficient at building galaxies than our models had suggested. One particularly striking discovery involved a galaxy observed by James Webb to exist when the universe was just 190 million years old. The galaxy, provisionally named JADES GSZ 13-0, appeared to be a mature, well-developed galaxy with a significant population of stars. If the observations were accurate, this galaxy would have contained perhaps 100 billion stars, comparable to the Milky Way, in an object whose light had been traveling toward us for more than 13 billion years. The existence of such a massive galaxy so early in cosmic history seemed to conflict with our understanding of how galaxies grow through the merging of smaller systems and the accretion of gas from the intergalactic medium. This is the true meaning of the phrase that is echoed through the halls of observatories and universities worldwide. James Webb looked too deep into space and found something shocking. It was not the shock of discovering alien life or signals from technological civilizations. It was not the shock of finding that our understanding of physics was fundamentally wrong. It was something more subtle and in many ways more profound. It was the shock of discovering that the universe was more complex, more mysterious, and less amenable to simple explanation than our theories had suggested. Let us pause here and contemplate what this means. For over a century, since Edwin Hubble demonstrated that the universe extended far beyond our galaxy, we have been constructing an increasingly detailed model of cosmic history. We have developed the Big Bang Theory, which explains how the universe expanded from an incomprehensibly hot and dense point. We have worked out the physics of the early universe with remarkable precision. We have traced the formation of the first atoms, the first molecules, the first stars, and the first galaxies. This edifice of understanding is built on careful observation, on mathematical rigor, on the accumulated knowledge of thousands of scientists working across generations. The theoretical framework that emerged from this work provided a coherent narrative of cosmic evolution that had successfully predicted many observational features of the universe. Yet here was James Webb, looking back through time at the epoch when galaxies were still being formed, and suggesting that our timeline might be wrong. Not catastrophically wrong, perhaps, but wrong enough to require reconsideration. The galaxies that existed in the first billion years of cosmic history appeared to be assembling themselves more quickly than we had predicted. Some of the observed galaxies possess such enormous masses that astronomers struggled to explain how they could have grown so large so quickly. The very fundamental processes by which galaxies merge and grow, processes that we thought we understood, seem to need revision. The universe, in its youthful phase, seemed to be behaving in ways that challenged our preconceptions. One might ask, in the face of such a discovery, whether this represents a failure of science. Does the gap between prediction and observation mean that our understanding was misguided? The answer is profoundly no. This is precisely how science operates at its finest. We construct theories based on the best available evidence. We make predictions. We design experiments or observations to test those predictions. When reality deviates from our expectations, we do not despair. Instead, we ask the most important question that science can ask: why? What aspect of our understanding is incomplete? What new physics, what new mechanisms, what new principles might explain what we are observing? This is the moment when science truly progresses, when the encounter with unexpected observations forces us to refine, revise, or potentially revolutionize our understanding. It is in this spirit that the astronomical community received the James Webb observations. Within weeks of the first images being released, hundreds of papers were submitted to scientific journals. Conferences were convened. Working groups were formed to analyze the data and develop new models. The data wasn't locked away as a secret or hidden because it contradicted theory. It was immediately shared with the global scientific community. Every researcher with the computational power to analyze it was invited to contribute their insights. This is the essence of how science operates when it is functioning at its best. It is a collective human endeavor, driven by curiosity and the desire to understand the universe as it actually is, not as we thought it should be. The community of astronomers and physicists worldwide engaged in a grand collaboration to make sense of what James Webb was revealing. As James Webb continued to observe, as more and more data accumulated, the picture became increasingly complex. The early universe revealed by the Space Telescope was not a pristine, orderly cosmos in which galaxies assembled themselves slowly and methodically according to simple rules. Instead, it was a chaotic, violent, dynamic place. Galaxies collided and merged. Black holes at the centers of galaxies blazed with tremendous power, ejecting jets of material at nearly the speed of light. Massive stars were born in prodigious numbers, and then exploded as supernovae, seeding the intergalactic medium with the heavy elements necessary for the formation of planets and, ultimately, life. The early universe was not a calm, peaceful realm, but a turbulent, energetic domain where matter was being continuously stirred, transformed, and redistributed. Let us consider for a moment what it means that we can see this. We could observe a scene that played out more than 13 billion years ago. The light that left those distant galaxies traveled to the expanding universe, to the vast cosmic web of dark matter and normal matter, past countless other stars and galaxies, until it finally reached our planet. And there it was captured by a mirror no larger than a human torso, a mirror that had been painstakingly constructed and positioned in space. The photons that strike that mirror once bounced off molecules in a galaxy so distant that its light left before the Earth itself had formed. And yet we can see it. We can detect it. We can study it. We can begin to understand what it tells us about the laws of physics that govern that distant realm. This capability seems almost miraculous when we pause to consider it fully. There is a nearly transcendent quality to this realization. We are creatures who have evolved on a small planetary sphere circling an ordinary star in one of 2 trillion galaxies. We have no obvious reason to expect that we should be capable of understanding the cosmos at all. The human brain is the product of millions of years of evolution shaped by survival pressures on the African savanna. There is no a priori reason that such a brain should be capable of comprehending the large-scale structure of the universe or the laws that govern it. Yet here we are, looking back to the universe's infancy, asking intelligent questions, and receiving answers. This seems to me to be perhaps the most remarkable fact about the human species, that we are capable of this at all. The observations from James Webb also revealed something unexpected about the distribution of galaxies in the early universe. The galaxies were not distributed uniformly throughout space. They showed clustering and alignment in ways that suggested the influence of the cosmic web, that vast network of dark matter that forms the gravitational scaffolding upon which all visible structure in the universe is built. The distribution of galaxies, their properties, their clustering patterns, all seem to point to a universe that was sculpted by invisible forces far more massive and far more pervasive than the ordinary matter we can see. Dark matter, that mysterious substance that comprises approximately 85% of the matter in the universe, was making itself known through its gravitational influence on the structures we could observe. Here we confront one of the deepest mysteries in modern physics. We know that dark matter exists. Its gravitational effects are everywhere we look. Without dark matter, galaxies would rotate too quickly and tear themselves apart. Without dark matter, galaxy clusters would not be held together by gravity. The large-scale structure of the universe, the cosmic web that James Webb helped us visualize, would not exist in its current form without dark matter. Yet we do not know what dark matter is composed of. We cannot directly detect it. We see only its shadow, its gravitational imprint on the matter we can perceive. It is as if the universe is playing a game with us, revealing the consequences of its presence, while carefully hiding its true nature. This fundamental mystery has persisted for decades. Despite tremendous effort from physicists worldwide, despite experiments of increasing sophistication, the true nature of dark matter remains elusive. It may be composed of exotic particles that barely interact with ordinary matter except through gravity. These hypothetical particles, with names like WIMPs, weakly interacting massive particles, or axions, could be streaming to our laboratories, to our bodies, at this very moment without leaving any trace of their passage. Alternatively, dark matter might be something we have not yet imagined, some form of matter or energy whose properties are so strange that they have escaped our previous attempts at detection. The James Webb observations did not solve this mystery, but they provided new constraints and new information that might eventually help us understand it. As we consider the implications of James Webb's observations, we must also acknowledge a parallel mystery that the telescope has not resolved but has perhaps deepened. This is the mystery of cosmic inflation. In the 1980s, a theoretical physicist named Alan Guth proposed that in the first fraction of a second after the Big Bang, the universe underwent an incomprehensibly rapid period of expansion. In less than a trillionth of a second, the universe expanded by a factor of 10 to the 26th power or more. This sounds like an outlandish fantasy, the desperate speculation of a theoretical physicist unburdened by observational reality. Yet the inflationary theory solved several profound mysteries about the universe. It explained why the universe appears so uniform on large scales. It explained the origin of the slight density fluctuations that eventually grew, through gravitational instability, into galaxies and galaxy clusters. It made specific predictions about the patterns of light and matter in the present-day universe that have been confirmed with remarkable precision by decades of observational data. Yet inflation also raises a troubling question. If the universe underwent such a dramatic expansion in the first fraction of a second, then everything we see today, every galaxy, every star, every atom in our bodies, originated from a subatomic region of space so small that quantum mechanical effects were dominant. This means that the distribution of matter and energy in the universe, which produced the galaxies we observe with James Webb, traces back to quantum fluctuations in the primordial universe. The entire structure of the cosmos, in some sense, is the product of quantum chance. The fact that we exist, that galaxies exist in the particular pattern and distribution that they do, may be the result of quantum events that occurred in the first fraction of a second after the Big Bang. Consider the implications of this realization. The galaxies that James Webb observes, the ones that challenge our theories of galaxy formation, may be the direct descendants of quantum fluctuations that occurred in the first billionth of a trillionth of a second after the Big Bang. The universe we perceive, the structures we observe and study, may be nothing more than one possible realization of quantum mechanics. In an infinite universe, generated by endless cycles of cosmic inflation, there may exist countless other universes with different physical laws, different configurations of matter and energy, leading to different structures and possibly different outcomes. This is a perspective that some physicists find compelling, but that remains highly speculative and controversial. This is the kind of thinking that separates modern cosmology from the observational astronomy of previous centuries. When our ancestors looked up at the night sky, they could catalog the positions of stars, measure their brightness, and wonder about their nature. With telescopes, we could resolve stars into individual points of light and determine their properties. With spectroscopy, we could analyze the light from distant objects and determine what elements they contained. But with modern theoretical cosmology informed by quantum mechanics and general relativity, we have come to understand that the universe itself may be far stranger and more profound than we ever imagined. We are not simply passive observers of a cosmos that exists independently of our theories. Our theories, our models, our observations form an intricate web in which understanding emerges from the interplay of data and theory. The James Webb Space Telescope, in looking deep into space and encountering galaxies that violate our expectations, has forced us to confront these deep questions anew. It is not simply a matter of adjusting a few parameters in our models of galaxy formation. It suggests that something more fundamental may be at stake. Perhaps the efficiency with which galaxies can form in the early universe is greater than we calculated. Perhaps the supply of available gas for star formation in the early universe was larger than we thought. Perhaps there are processes occurring in the first billion years of cosmic history that we have not yet identified. Perhaps our understanding of the dark matter that dominates the universe's mass is incomplete in ways that affect how galaxies form and evolve. One area that has attracted considerable attention from astronomers analyzing James Webb data is the role of supermassive black holes in the early universe. In the present-day universe, nearly every large galaxy appears to contain a supermassive black hole at its center. These black holes range in mass from millions to billions of times the mass of the Sun. The supermassive black hole in the center of our own galaxy, the Milky Way, is known as Sagittarius A*, and has a mass of approximately 4 million solar masses. When these black holes are actively accreting material, they can become incredibly luminous, outshining the galaxies that contain them. Such objects are called quasars or active galactic nuclei. The energy output from an active galactic nucleus can be truly staggering, with a single quasar potentially outshining an entire galaxy containing hundreds of billions of stars. The existence of supermassive black holes in the present-day universe has been established beyond doubt. We have observed the orbits of stars circling the supermassive black hole in our own galaxy and have used their orbital properties to determine its mass with high precision. We have observed jets of material ejected from active galactic nuclei traveling at nearly the speed of light. We have detected the gravitational influence of supermassive black holes on the motion of stars and gas in galaxies. But the supermassive black holes in the early universe present a puzzle. How did they grow to such enormous sizes so quickly? A black hole in the center of a galaxy observed by James Webb to exist when the universe was less than 1 billion years old would have needed to accumulate 1 billion solar masses in its gravitational embrace in a time span that, from a cosmic perspective, was extraordinarily brief. The timescale problem is profound. In the present-day universe, black holes grow primarily through two mechanisms: accretion of material from their surroundings and mergers with other black holes. Both processes are slow from a cosmic perspective. A black hole typically doubles its mass over a timescale of millions or billions of years, depending on the efficiency of the accretion process. Yet the observed supermassive black holes in the early universe seem to require growth timescales of millions of years at most to reach the masses we observe. This seems to require either an extraordinarily efficient accretion process or multiple rapid mergers, or some combination thereof. There are several possible explanations for this observation. Perhaps supermassive black holes can grow through processes that are more efficient than the standard models suggest. Perhaps the density of material available for accretion in the early universe was so much higher that black holes could consume material at truly prodigious rates. Perhaps they can form through the direct collapse of massive clouds of gas, rather than through the gradual accretion and merger of smaller black holes. When a cloud of primordial gas, composed entirely of hydrogen and helium, collapses, it may be possible for it to collapse directly into a black hole without first going through an intermediate stellar phase. Such primordial black holes could then grow through accretion and mergers. Perhaps supermassive black holes form very early in cosmic history, in the first galaxies, and then grow primarily through mergers as those galaxies collide and combine. Each of these possibilities has implications for our understanding of how the first galaxies form and evolve. The study of active galactic nuclei in the early universe using James Webb's infrared sensitivity, has revealed that some of the earliest galaxies were undergoing tremendous growth. The central engines of these galaxies were burning, powered by infalling material, and the conversion of gravitational potential energy into radiation. This radiation, in many cases, was powerful enough to affect the entire galaxy. Jets from the black hole could compress gas clouds, triggering bursts of star formation, or conversely, they could heat the intergalactic medium and suppress further growth of the galaxy. These processes, known as feedback mechanisms, are crucial for understanding why galaxies evolved as they did. The black holes and the galaxies they inhabit exist in a symbiotic relationship, with each influencing the development of the other. James Webb's observations have revealed that such feedback was active in the early universe, just as it is today. Galaxies were not simply assembling themselves passively. They were dynamically regulating their own growth through the interplay of gravity, radiation, and the mechanics of accretion onto black holes. The universe was more dynamic, more interactive, more alive with processes than we had appreciated. And while this does not solve the fundamental mystery of how supermassive black holes grew so large so quickly, it provides us with important clues about the mechanisms at work. As we contemplate these findings, we might pause to reflect on what they tell us about the nature of scientific knowledge and cosmic history. The universe, we are learning, is not a simple machine that obeys a few basic rules from which everything else can be deduced. It is a complex, multifaceted system with numerous interacting components. The formation of galaxies, the growth of black holes, the distribution of dark matter, the role of radiation and gravitational feedback, all of these elements interact in ways that are difficult to predict and even more difficult to reverse engineer from observations. This is not a failure of science. It is rather the recognition that reality is rich and intricate in ways that theoretical models must account for. The job of the scientist becomes not to reduce the universe to a handful of simple principles, but to understand the consequences of those principles as they play out in the complexity of the real cosmos. There is another domain where James Webb's observations have provided surprising insights: the formation of stars in the early universe. When we observe the universe today, we find that the rate at which stars form in galaxies varies tremendously. In some galaxies, star formation is occurring at a brisk pace, with billions of stars being born each year. In other galaxies, star formation has largely ceased, and the galaxy is a relatively quiet collection of old stars slowly cooling and fading. The rates of star formation in galaxies, and how these rates have evolved over cosmic time, are crucial for understanding the history of the universe. By measuring the cosmic star formation rate, the total rate at which stars are being formed in all galaxies in a given volume of the universe, astronomers can piece together the history of how the universe transformed from a mostly empty realm to one filled with billions of galaxies. For many decades, astronomical observations suggested that the cosmic star formation rate peaked about 3 to 4 billion years after the Big Bang and then gradually declined. This pattern, if true, would suggest that the earliest galaxies were not particularly vigorous at forming stars, and that star formation became more efficient as the universe aged and galaxies had more time to develop. However, James Webb's observations have suggested a more complicated picture. The earliest galaxies, those observed to exist when the universe was less than 500 million years old, appear to have been quite active in star formation. They were producing stars at rates that, adjusted for their total mass, were comparable to or even exceeded the star formation rates observed in galaxies that formed later in cosmic history. This finding has profound implications. If the earliest galaxies were capable of star formation rates as high as we are now measuring, then they must have been capable of processing large quantities of gas into stars very rapidly. This suggests either that these galaxies had access to substantial amounts of gas that could be converted into stars, or that the processes governing how quickly gas is converted into stars were different in the early universe than they are in the present day. It also suggests that these galaxies, despite their young age in cosmic terms, had already undergone significant chemical evolution. The heavy elements that we observe in these galaxies, the carbon, nitrogen, oxygen, silicon, and iron that are essential for the formation of terrestrial planets and the emergence of life, must have been produced in a previous generation of stars and then incorporated into the current population of stars and galaxies we observe. Here we encounter a profound mystery that James Webb has illuminated but not resolved. If the universe is only a few 100 million years old when we observe these galaxies, how could those galaxies already contain significant abundances of heavy elements? Such elements can only be produced through nucleosynthesis in the cores of massive stars. Massive stars burn through their fuel and explode as supernovae within a few million years of their formation. The timescale for producing heavy elements and then incorporating them into a new generation of stars is measured in tens of millions of years at minimum. Yet the observations suggest that this cycle of star formation, nucleosynthesis, and incorporation of heavy elements into new stars must have occurred, perhaps multiple times, and a time span of just a few 100 million years. One possible resolution to this puzzle is that the earliest stars in the universe form very rapidly, almost immediately after the Big Bang. The first stars would have been composed entirely of primordial hydrogen and helium, the only elements that existed before any stars ignited their nuclear furnaces. These population 3 stars, as they are termed in astronomical nomenclature, would have been tremendous in size, perhaps 1,000 times the mass of our Sun. Such stars would have burned their fuel in just a few million years. When they exploded as supernovae, they would have seeded the intergalactic medium with heavy elements. A subsequent generation of stars, the population 2 stars, would have formed from this enriched material and would themselves eventually expire as supernovae, further enriching the environment. By the time we observe galaxies with James Webb, we are perhaps seeing galaxies populated by stars from multiple generations, all of which have formed within the first few 100 million years of cosmic history. This scenario, while theoretically sound, pushes the boundaries of what we thought possible in the early universe. It suggests that star formation was occurring with tremendous vigor in the first few 100 million years after the Big Bang. It suggests that the universe, from a very early epoch, was not a quiescent realm of slowly evolving structures, but rather a dynamical, turbulent place where matter was being rapidly processed into stars, and stars were dying in catastrophic explosions. It is a vision of the early universe as a more violent and more energetic place than some of our earlier models had suggested. The implications extend further still. If stars and galaxies were forming so rapidly in the early universe, then the production of heavy elements must also have been rapid. This means that the conditions for the emergence of chemistry beyond simple atomic species, for the formation of molecules, for the development of carbon-based chemistry that might be the foundation for life, were established much earlier in cosmic history than we had previously appreciated. The dust grains that would form the cores of planetary systems, the complex organic molecules that would eventually seed the interstellar medium and deliver the building blocks of life to nascent planets, may have been abundant in the universe far earlier than we thought. When we step back and consider the full implications of James Webb's observations, a remarkable picture emerges. The universe, in the first billion years after the Big Bang was a far more sophisticated, far more complex place than our earlier models suggested. Galaxies were assembling themselves, black holes were igniting at their centers, massive stars were forming and dying, heavy elements were being produced and distributed into space. The chemistry of the universe was becoming more varied and more interesting. The raw materials from which planets would form were being created. And although James Webb has not detected life itself in the early universe, such a discovery would be revolutionary and would require observations and analyses far beyond our current capabilities. It is revealed that the universe was preparing the stage for life's emergence. This brings us to consider a broader question that James Webb's observations raise implicitly, if not explicitly. If galaxies and stars and the chemical elements necessary for life were all present in the early universe, what does this tell us about the prevalence of life itself in the cosmos? This is not a question that James Webb was designed to answer, and indeed, the observations it has made do not directly address the question of whether life exists elsewhere in the universe. But they do provide context for contemplating this question. For centuries, philosophers and astronomers have speculated about whether Earth harbors the only instance of life in the universe, or whether the cosmos is teeming with life. In the 20th century, the prevailing view among many scientists was that the conditions for life were so stringent, so requiring of a specific set of circumstances, that Earth was probably unique or nearly so. Life was thought to require a planet at just the right distance from its star, with just the right atmospheric composition, with just the right amount of geological activity to maintain a dynamic environment. The universe, from this perspective, was mostly dead, with life being a rare and precious exception to the general rule of cosmic barrenness. However, as our knowledge of the universe has expanded, as we have discovered thousands of exoplanets and learned that planets are vastly more common than we once thought, this perspective has shifted. We now know that planetary systems are common. We now understand that the chemical elements necessary for life are distributed throughout the universe. We now recognize that the conditions for life, while not trivial, are probably more common than was previously supposed. The discovery of potentially habitable exoplanets, worlds that orbit in the habitable zone of their host stars, where conditions might allow liquid water to exist on the surface, has become routine. Thousands of such worlds have been identified in recent years. James Webb's observations add a new dimension to this line of reasoning. If the universe was producing heavy elements, forming planetary systems, and developing complex chemistry in the first billion years after the Big Bang, then the potential for life to emerge might have existed far earlier in cosmic history than we had thought. If life requires chemistry based on carbon, oxygen, nitrogen, and other heavy elements, then perhaps life could have originated in galaxies that existed when the universe was less than 1 billion years old. Perhaps, in the present day, after more than 13 billion years of cosmic history, the universe is filled with life, with civilizations, with technological societies at various stages of development. We do not know this to be true. The mere presence of the chemical elements necessary for life is not the same as the presence of life itself. There are additional factors that influence whether life can emerge and persist. The stability of planetary systems, the presence of appropriate planetary environments, the chemical processes that lead from simple molecules to self-replicating systems, the emergence of biological complexity through evolution. All of these are aspects of the puzzle that James Webb's observations do not directly address. Moreover, there is the question of whether the timescales are sufficient. Even if life can emerge in simple chemical systems and then evolve through natural selection, the process of evolution from simple microbes to intelligent beings capable of technology may require billions of years. The evolution of complex life on Earth took roughly 4 billion years. There may not have been sufficient time in the first billion years of cosmic history for complex intelligent life to emerge, though simpler forms of life might have had time to develop. Yet the fact remains that James Webb has revealed a universe in which the possibilities for life are more extensive than we had previously appreciated. It has shown us that the universe, even in its youth, was diverse, complex, and dynamical. It has demonstrated that the raw materials for life, the heavy elements, the complex chemistry, the dynamic environments, were being produced and distributed with sufficient rapidity that life may have had multiple opportunities to emerge at different times and places throughout cosmic history. As we gaze at the images from James Webb, we are struck by a sense of profound humility. We are looking back to a time when our galaxy had not yet formed, when our star was not yet ignited, when our planet was still in the realm of possibility rather than reality. The photons we are detecting left distant galaxies more than 13 billion years ago, long before the Sun was born, long before the Earth coalesced from a disk of dusty gas circling the young Sun. And yet we can see them. We can analyze them. We can begin to understand them. This is a remarkable achievement of human civilization, the development of instruments and theoretical frameworks that allow us to peer so far into space and time. But there is something else at stake in these observations, something that transcends the merely technical or scientific. There is a deeper existential question embedded in James Webb's observations of the early universe. It is the question of how we, beings born from the matter of the cosmos, come to understand the cosmos itself. We are made of stardust, in the most literal sense. The carbon in our bodies was forged in the cores of distant stars. The oxygen in our blood was created in stellar furnaces. The iron in our blood, the calcium in our bones, the phosphorus in our cells, all of these elements were synthesized in stars and distributed through the cosmos by stellar explosions. We are not separate from the universe. We are part of it, fashioned from its substance, animated by the same physical laws that govern the motion of galaxies and the birth and death of stars. This recognition carries with it a profound sense of kinship with the cosmos. When James Webb observes a distant galaxy, and we analyze the light from that galaxy to understand its properties, we are in a sense the universe understanding itself. Consciousness, intellect, curiosity, these faculties that we often think of as transcending the material world, as being somehow separate from or above the physical universe, are themselves manifestations of physical processes. They emerge from matter arranged in certain configurations. They are as much a part of nature as the expansion of space or the gravitational collapse of gas clouds into stars. The realm of consciousness and the realm of physics are not two separate domains, but different aspects of a unified reality. There is a philosophical perspective, sometimes called cosmic naturalism or naturalistic pantheism, that takes this realization seriously. From this perspective, the universe is not a collection of dead, inert matter moving according to mechanical laws. Rather, the universe is understood as a living, dynamic whole that expresses itself in myriad ways, in the motion of planets, in the birth and death of stars, in the emergence of life, in the development of consciousness. We are not observers standing outside the universe, looking in. We are expressions of the universe, windows through which it perceives itself. This is not to say that consciousness is a fundamental property of matter, present everywhere from the smallest subatomic particle to the largest galaxy. That would be a kind of panpsychism that is difficult to justify empirically. Rather, it is to acknowledge that consciousness is a natural phenomenon, arising through physical processes and not violating any laws of physics. And once consciousness emerges, once there are beings capable of thought, language, and abstract reasoning, the universe gains the capacity to reflect upon itself, to study itself, to develop theories about its own structure and history. Carl Sagan expressed this idea beautifully when he reflected on the fact that humans are capable of understanding the universe. He noted that the universe is vast and human beings are small, yet we are capable of contemplating the cosmos and, to a surprising extent, of understanding it. This capacity seems almost improbable until we realize that humans are made of the same atoms, governed by the same laws, as the rest of the universe. The atoms that comprise our brains have been cycling through the cosmos since the early universe. They have been incorporated into stars, scattered across space in supernova explosions, collected into planets, and finally assembled into the organized patterns that constitute human consciousness. There is nothing improbable about matter assembled in certain ways coming to understand other matter assembled in different ways, because it is all part of the same universe, following the same laws. When we consider this perspective, James Webb's observations take on an additional layer of significance. We are not simply acquiring information about distant objects. We are participating in the universe's self-knowledge. We are using the universe's own laws of physics and chemistry to construct instruments that allow us to perceive the universe. We are using our consciousness, which arises from matter, to understand matter arranged in different configurations at different places and times. We are, in the fullest sense, part of the universe knowing itself. This participation connects us to the cosmos in ways that are both profound and humbling. This realization carries both a sense of wonder and a sense of responsibility. The wonder comes from the recognition of our deep kinship with the cosmos, from the understanding that we are not aliens in a foreign universe, but expressions of the universe itself. The responsibility arises from the understanding that if we are the universe aware of itself, then what we do matters not just to us, but to the universe as a whole. The choices we make about how to treat our planet, about how to develop our knowledge and technology, about how to relate to each other and to the living world, these are choices that affect the future of the cosmos in whatever infinitesimal way the actions of a small species on a small planet can do so. We are custodians not just of our own world, but of a fragment of the universe that has become conscious. Let us return now to the specific observations from James Webb and consider what they tell us about the immediate future of astronomy and cosmic studies. The discoveries made by James Webb in its first year of observations have generated thousands of questions and hundreds of research projects. Scientists worldwide are analyzing the data, developing new models, proposing new observations to test their ideas. The pipeline of science that will emerge from James Webb data will likely keep the astronomical community occupied for decades. Among the most exciting prospects is the possibility of detecting the very first galaxies, the first objects to form after the Big Bang that were massive enough and bright enough to ionize the hydrogen gas that filled the early universe. There was a period between about 300,000 years after the Big Bang and roughly 1 billion years after the Big Bang, during which the universe transitioned from being completely opaque to ionizing radiation to being transparent. This period is called the epoch of reionization, and understanding it is a major goal of current observational cosmology. The universe was initially opaque because it was filled with neutral hydrogen atoms, which strongly absorb ultraviolet light. As the first stars formed and began to emit ultraviolet radiation, they gradually ionized the hydrogen gas, making it transparent. James Webb is uniquely positioned to detect the faint light from the first galaxies, and to map out how the universe's transparency to radiation gradually increased over time as more and more galaxies formed, and their ionizing radiation cleared the intergalactic hydrogen. Similarly, James Webb's observations of galaxies at intermediate distances, those observed when the universe was between 1 and a few billion years old, are providing constraints on how galaxies evolve over cosmic time. By comparing the properties of galaxies at different cosmic epochs, astronomers can measure how galaxies grow, how they transform, and how they contribute to the large-scale structure of the universe. This is not a passive process of observation. It is an active interrogation of cosmic history, a conversation between theory and observation in which each informs and refines the other. Researchers construct models of galaxy evolution and use them to make predictions about what James Webb should observe. When observations deviate from predictions, the models are revised. New observations are designed to test the revised models. This iterative process drives progress in our understanding. Another area of significant scientific interest enabled by James Webb is the study of nebulae within our own galaxy where stars are currently forming. The Orion Nebula, the Pillars of Creation, the Carina Nebula, these are regions of space where massive clouds of gas are collapsing under gravity, heating up, and eventually igniting nuclear fusion at their cores to become stars. James Webb's infrared sensitivity allows it to see through the dust that obscures these regions from optical telescopes. The dust, composed of tiny grains of silicates and carbon compounds, is created in the atmospheres of dying stars and ejected into space. This dust accumulates in molecular clouds and eventually collapses along with the gas to form stars and planets. Optical light cannot penetrate the dust, but infrared radiation, with its longer wavelength, passes right through. James Webb's images of star-forming regions are of breathtaking clarity and detail, revealing the architecture of stellar nurseries and the processes by which stars are born. These observations serve a dual purpose. On the one hand, they directly answer scientific questions about how stars form, about the masses of newborn stars, about the disks of material surrounding young stars from which planets will eventually emerge. On the other hand, they provide insights that inform our understanding of the distant past. The processes by which stars form today are presumably similar to the processes by which stars formed in the early universe, with some modifications arising from the different physical conditions. In the early universe, the gas was composed entirely of hydrogen and helium. In the present day, the gas contains a small but significant fraction of heavier elements, which affects how quickly it cools and how easily it fragments into stars. By studying star formation in our own galaxy with James Webb, we are learning principles that help us interpret observations of star formation in the distant early universe. Let us consider now a question that naturally arises from James Webb's observations. What comes next? James Webb has demonstrated that the technology for detecting infrared radiation from distant galaxies works, and works beautifully. But the universe is vast, and even James Webb can only observe a tiny fraction of the sky in any given period of time. To map out the full extent of the early universe, to understand the complete history of galaxy formation, to address the mysteries that James Webb has revealed, we will need additional observations, additional instruments, and additional space telescopes. There are indeed plans for successors to James Webb, though these are still largely in the conceptual and planning stages. A proposed successor called the Nancy Grace Roman Space Telescope, which is expected to launch in the coming years, will complement James Webb's observations. Roman will have a wide field of view, allowing it to survey large areas of sky and identify the most distant and interesting objects for more detailed study by James Webb or other instruments. There are also plans for future generations of extremely large ground-based telescopes, such as the Extremely Large Telescope and the Giant Magellan Telescope, which will provide observations of distant galaxies in visible and near-infrared light, complementing James Webb's infrared observations. These telescopes are being constructed at remote sites with thin, dry atmospheres to minimize the distortion caused by atmospheric turbulence. But beyond these specific missions, there is a broader question about how humanity should approach the study of the cosmos in the coming decades and centuries. James Webb has demonstrated the power of large, complex, ambitious projects that require sustained commitment and substantial resources. The telescope was originally estimated to cost around $500 million, but eventually cost nearly $10 billion. The engineering challenges were immense, and many experts doubted whether the mission would ever succeed. Yet the scientific returns have already justified the investment many times over. The observations from James Webb are revolutionizing our understanding of the early universe. This raises a philosophical question about priorities and values. Is it appropriate for humanity to invest such enormous resources in studying the cosmos when there are pressing problems here on Earth: poverty, disease, climate change, social injustice? This is a fair question, and one that deserves serious consideration. However, it is worth noting that the total cost of James Webb, while substantial, represents a tiny fraction of global economic output or even of government spending in developed nations. It represents less than 1% of the annual budget of NASA, which itself receives less than 1% of the U.S. federal budget. The resources devoted to space telescopes, while significant, do not come at the direct expense of addressing earthly problems. One does not choose between funding James Webb and funding healthcare or education or environmental protection. These are separate decisions, governed by different political and economic processes. Moreover, there is an argument that the pursuit of knowledge about the cosmos has value in itself, quite apart from any practical applications. Humans have always sought to understand the world around them, to make sense of their place in the universe. The pursuit of knowledge is part of what makes us human. Science, in its ideal form, is a collective human endeavor to understand reality as accurately as possible. This endeavor is not separate from our other values and goals. Rather, it is intertwined with them. A civilization that pursues truth and understanding is more likely to make wise decisions about how to address its problems than a civilization that remains in ignorance. The history of human progress shows that advances in fundamental science often lead, unexpectedly, to practical applications that improve human life. There is also a pragmatic argument that space exploration and astronomy have yielded numerous technological developments that have applications here on Earth. Many technologies that are now commonplace were originally developed for space missions. Material science, electronics, computing, medical technologies, all have benefited from the demands of space exploration. The same infrared detectors that James Webb uses to observe distant galaxies are the descendants of detectors developed for thermal imaging, and that are now used in medical imaging and thermal sensing. The engineering innovations required to build and operate James would have applications far beyond astronomy. The advanced materials, the precision manufacturing techniques, the computer systems, all of these represent advances that ripple outward into society. But perhaps the most profound argument for why humanity should continue to invest in cosmic exploration and astronomy is the existential and psychological one. We are creatures who are driven by curiosity. We want to understand the world and our place in it. We want to know where we came from and where we are going. These questions are not frivolous or marginal to human existence. They are central to what it means to be human. By pursuing answers to these questions through science and reason, we are expressing something fundamental about our nature. Moreover, there is a perspective that suggests that the study of the cosmos puts terrestrial problems into a useful context. When we contemplate the vastness of space and the tremendous ages of the universe, our parochial concerns, the political disputes that divide nations, the economic competitions that drive conflict, the petty grievances that separate groups of people, come to seem less important. Not that they are unimportant. The suffering of individuals and the well-being of communities matter tremendously. But when we understand ourselves as part of a cosmos billions of years old, contain billions of galaxies, we can perhaps develop a perspective that allows us to work together to address our common problems and common future. The unity of humanity becomes apparent when we see ourselves as inhabitants of one small planet in a vast cosmos. James Webb's observations have also provided new evidence relevant to a question that has occupied philosophers and theologians for millennia. Are we alone? The telescope has not detected life elsewhere in the universe. It has not confirmed the existence of intelligent beings on exoplanets, or received any signals from technological civilizations. But it has revealed that the universe was preparing the stage for life far earlier and more extensively than we had thought. It has shown that the chemical elements necessary for life were abundant in the early universe, that galaxies with complex chemistry and dynamic environments existed in the first billion years of cosmic history. The raw materials and the environmental conditions that we know are associated with life on Earth appear to have been common throughout the universe. This does not prove that life is abundant in the universe. The emergence of life requires more than just the right chemistry and the right environmental conditions. It requires specific chemical processes that we still do not fully understand. The transition from simple chemistry to biochemistry, the emergence of self-replicating molecules, the development of molecular machinery to support life. These are all steps in a complex process that we have barely begun to understand. It requires the emergence of genetic systems that can store information and pass it from generation to generation. It requires billions of years of evolution to produce complex organisms and eventually intelligent beings. Many of these steps may be very rare. The history of life on Earth suggests that the emergence of intelligence is not inevitable, even in an environment where life appears and thrives. For billions of years after life emerged on Earth, the only living things were microscopic organisms. Intelligent life only emerged recently in geological time, and technological civilization more recently still. Yet the fact remains that James Webb has revealed a universe in which the conditions for life appear to have been widespread throughout cosmic history. Even if the emergence of intelligent life is a very rare event, the sheer size of the universe and the vast span of cosmic time suggests that life, and possibly intelligent life, may have emerged in multiple places. As Carl Sagan famously observed, given the billions of galaxies and the billions of stars in each galaxy, it would seem like a terrible waste of space if life emerged only on our small planet. James Webb's observations reinforce this intuition by showing that the universe was far more active and dynamic in producing the building blocks of life than we had previously appreciated. The question of extraterrestrial life remains open, and James Webb cannot directly answer it. To detect life on distant exoplanets would require observing the atmosphere of such planets and identifying biosignatures, chemical compositions that could plausibly only be produced by living processes. Examples of potential biosignatures include oxygen combined with methane, which would be unstable and require constant replenishment, or other combinations of gases that cannot easily be produced through non-biological chemistry. The challenge is that to examine the atmosphere of a planet orbiting a distant star, we must rely on the light from that star passing through the planet's atmosphere, and the signatures of the atmosphere are extremely subtle. James Webb does have the capability to analyze the atmospheres of some exoplanets, particularly those that are relatively large and that orbit close to their stars. The reflected or transmitted starlight can be analyzed spectroscopically to determine the composition of the planet's atmosphere. But detecting the atmosphere of a small Earth-like planet orbiting at a distance comparable to Earth's distance from the Sun is beyond the current capabilities of even James Webb. Such observations will likely require future space telescopes with even greater sensitivity, or perhaps ground-based observatories with sophisticated adaptive optics systems. Nevertheless, the prospects for eventually detecting life elsewhere in the universe, through atmospheric studies or other means, have become more promising as a result of James Webb's observations and other recent developments in astronomy. We are entering an era in which the question of whether Earth harbors the only instance of life in the universe may transition from a metaphysical or theological question to an empirical one that can be addressed through observation and scientific method. This is a remarkable transition that would have been unimaginable just a few decades ago. As James Webb continues to operate and gather data, it will undoubtedly make additional discoveries that we cannot anticipate. Science progresses not only through the confirmation of existing theories, but also through surprising discoveries that overturn our expectations. James Webb has already provided such surprises, revealing galaxies that are more massive and more mature than our models predicted, detecting active galactic nuclei in the early universe, showing that star formation was vigorous in the first billion years after the Big Bang. As the telescope observes more of the universe, as astronomers develop more sophisticated tools for analyzing the data, additional surprises are likely to emerge. What gives us confidence that future observations will be interesting and will advance our understanding is the history of astronomy itself. Again and again, when we have developed a new observational capability or improved an existing one, we have discovered things we did not expect. Galileo pointed his primitive telescope at the moon and saw mountains and valleys instead of a smooth sphere. He observed the moons of Jupiter and realized that not all celestial bodies orbit the Earth. These observations contradicted the prevailing understanding of the cosmos and opened new lines of inquiry. In the 20th century, the development of radio astronomy revealed a universe invisible to optical telescopes, a universe of quasars and pulsars and cosmic radiation. The discovery of the cosmic microwave background radiation, the afterglow of the Big Bang, revolutionized our understanding of cosmic history. With each new window into the universe, we have discovered structure and complexity that we had not imagined. There is no reason to believe that James Webb will be an exception to this pattern. The telescope is revealing the early universe in detail never before possible. As we study these observations and develop our understanding, new questions will emerge. New mysteries will become apparent. New observational programs will be designed to address these mysteries. The process of science, of asking questions, making observations, developing theories, and generating new questions, will continue. In contemplating the implications of James Webb's observations, we are forced to grapple with questions about the nature of time itself. The light reaching us from distant galaxies has been traveling through space for billions of years. In a very real sense, we are observing the past. But what does it mean to observe the past? Does the light carry with it information about events that happened in the distant past, or are we simply preceding the current state of light waves that have been traveling through space? Is time a linear progression from past through present to future, or is it something more complex and subtle? These questions touch on deep issues in the philosophy of physics. In Einstein's theory of relativity, the distinction between past, present, and future is less absolute than in Newtonian mechanics. The order of events can appear different to different observers depending on their state of motion. There is a concept called the light cone, the region of space-time that can affect or be affected by a given event. The light cone of an event in the distant past extends to include our present position in space-time, which is why we can observe that distant past event. But the light cone of an event in the far future does not yet include our current position, so we cannot observe future events. Time, in this relativistic framework, is intimately tied to causality and the structure of space-time. James Webb's observations provide us with a window into the causal past of our own region of space-time. The light it observes from distant galaxies represents events that are in the causal past of our current moment. These events have already occurred, from the perspective of relativistic physics. The light has reached us, and we can extract information from it. But the events themselves, the formation of the galaxies, the birth of stars within those galaxies, the interactions between matter and radiation in the early universe, these events are not occurring now from our perspective. They occurred billions of years ago. Yet through the light they emitted, we can learn about them. This is perhaps the most profound aspect of astronomy in general, and of James Webb's observations in particular. We are not merely studying static objects that exist somewhere in space. We are studying the history of the universe. We are reading the cosmic record book, written in the light and particles that reach us from across space. Every galaxy that James Webb observes is a window into a different cosmic epoch. By comparing the properties of galaxies at different distances, and therefore at different times in cosmic history, we can reconstruct the history of the universe. We can understand how the cosmos has evolved from a hot, dense, nearly uniform state shortly after the Big Bang to the rich tapestry of structure and complexity we observe today. Let us consider for a moment the philosophical implications of this capability. For most of human history, we could only observe our immediate surroundings. We knew nothing of the world beyond our local region. The development of telescopes extended our vision, but only to nearby objects. The realization that there were other galaxies beyond our own came less than a century ago. The recognition that the universe had a beginning and has a history of evolution came even more recently. And now, with James Webb, we have the capability to observe merely all the way back to the beginning, to see the universe in its infancy. This represents a tremendous expansion of human knowledge and understanding. Yet it also raises a humbling question. Is this really the beginning? James Webb can observe to within a few 100 million years of the Big Bang, but it cannot observe the first moments themselves. The era of the universe between the Big Bang and the time when the first stars and galaxies formed remains largely opaque to our observations. During this period, the universe was filled with ionizing radiation and hot plasma. Galaxies could not form until the universe had cooled sufficiently and atoms could combine to form neutral atoms. The light from this era has been stretched by the expansion of the universe into wavelengths that are difficult to detect. In principle, the light from the very earliest moments of the universe is still present around us in the form of the cosmic microwave background radiation, the cooling remnant of the Big Bang. But extracting detailed information about the structure of the universe during its first few 100 million years, beyond what we already know from the cosmic microwave background, is extraordinarily challenging. Moreover, there is a fundamental limit to how far back we can observe, and posed by the nature of quantum mechanics. Before the universe was about 10 to the power of -43 seconds old, the density and temperature were so extreme that quantum gravity effects became important. In this regime, the laws of physics, as we currently understand them, break down. The combination of quantum mechanics and general relativity produces infinities and paradoxes that we do not know how to resolve. This era, called the Planck era, remains beyond our current understanding. We have no observations of this period. It may be fundamentally unobservable, a point of absolute ignorance in our knowledge of the universe. This recognition of the limits of our knowledge is not a failure of science or of James Webb. Rather, it is a testament to the epistemological humility that should characterize any serious attempt to understand the universe. We can learn a tremendous amount through observation and reason. We can reconstruct much of the universe's history. But there are limits to what we can know. There are questions that, with our current understanding, may be fundamentally unanswerable. This does not diminish the value of the knowledge we do have. Rather, it places that knowledge in proper perspective. We exist at a particular point in human history, with particular capabilities and particular limitations. The questions we cannot yet answer may yield to future generations with better tools and deeper insights. As we reflect on James Webb's observations and their implications, we return to the profound realization that the universe is comprehensible to human minds. This is a remarkable fact. The brain of a human being occupies a volume of about 1,400 cubic centimeters and weighs about 1.5 kilograms. It is composed of approximately 86 billion neurons, each of which is connected to tens of thousands of other neurons. This 3-pound mass of organized matter has somehow developed the capability to contemplate galaxies billions of light years away, to understand the laws of gravity and quantum mechanics, to develop technologies that allow us to observe phenomena at the edge of the observable universe. The physicist Eugene Wigner wrote an essay titled, "The Unreasonable Effectiveness of Mathematics in the Natural Sciences," in which he expressed wonder at the fact that abstract mathematical concepts developed by human mathematicians turn out to describe natural phenomena with extraordinary accuracy. The theory of general relativity, developed by Einstein as a geometric description of space-time, provided a framework for understanding gravity. The Schrödinger equation, developed as a mathematical description of quantum systems, turned out to accurately predict the behavior of atoms and subatomic particles. Non-Euclidean geometry, developed as pure mathematics without physical application in mind, later became essential for understanding curved space-time. It is as if the universe is written in the language of mathematics, and humans have somehow learned to read this language. This capability is the more remarkable when we recognize that humans evolved to survive on the African savanna, where the problems of daily life involve finding food, avoiding predators, and reproducing. There was no obvious evolutionary advantage to being able to understand abstract mathematics or to comprehend the structure of the universe. And yet we possess this capability. Perhaps it is an accident of evolution, a byproduct of the general-purpose intelligence that was advantageous for survival. Or perhaps, as some philosophers suggest, there is something special about the universe itself, something that makes it comprehensible to beings who arise within it. Whatever the explanation, the fact remains that we can understand the universe, and that understanding is deepened dramatically with instruments like James Webb. The images and data from James Webb will be studied for decades and centuries to come. Future generations of astronomers will analyze the data, develop new theories, conduct new observations, and push our understanding further. But the fundamental significance of James Webb's observations lies not in any single discovery or finding. Rather, it lies in the expansion of human knowledge and the deepening of our understanding of our place in the cosmos. We have looked deep into space, back to a time when the universe was young, when galaxies were still assembling themselves, when the universe was preparing the stage for the eventual emergence of life and intelligence. What we have found is a cosmos that is stranger, more complex, and more wonderful than we had imagined. We have found a universe in which the possibility for life seems more widespread than we had thought. We have found that the early universe, rather than being a peaceful place of slow cosmic evolution, was a dynamic and turbulent realm where matter was being rapidly transformed. We have found evidence that supermassive black holes played a crucial role in the evolution of galaxies from the earliest cosmic times. We have found that our current theories, while impressive in their explanatory power, have limits and mysteries that remain to be solved. And in all of this, we have been reminded that we are part of this universe. The atoms that comprise our bodies were manufactured in stellar photosis billions of years ago and distributed across space by stellar explosions. The carbon, oxygen, nitrogen, and phosphorus that are essential for life were created through cosmic processes that James Webb is helping us understand. We are made of the universe, and we are capable of understanding the universe. This creates a kind of cosmic consciousness, a feedback loop in which the universe has become aware of itself to our minds and our instruments. As we stand at this moment in history, with James Webb returning unprecedented observations of the early universe, we can reflect with gratitude on the enormous effort that went into creating this instrument and releasing it to the stars. We can look with hope to the future, knowing that the mysteries revealed by James Webb will drive new observations, new theoretical developments, and new understanding. And we can view with wonder the universe itself, a cosmos so vast, so ancient, so rich with structure and complexity, yet comprehensible through the exercise of human reason and creativity. The journey of understanding the cosmos is far from complete. James Webb has taken us deeper into space and further back in time than ever before, but there remains much to explore, much to understand, much to discover. The universe will continue to surprise us, to humble us, to inspire us to push further, to ask deeper questions, to seek greater understanding. And as long as we maintain the curiosity that has driven us to build instruments like James Webb, as long as we have the courage to face the unexpected and the unknown, we will continue to grow in our understanding of the cosmos and our place within it. This is the gift that James Webb has given us, not final answers, but better questions, and the tools to pursue those questions wherever they may lead. The telescope has shown us that the universe's history is richer and more complex than we had anticipated. It has revealed that our planet, our sun, our galaxy, and our species are embedded in a cosmos that is actively evolving, constantly changing, and endlessly surprising. The shock that James Webb found when it looked too deep into space is the shock of recognition that we live in a universe far more magnificent and mysterious than we had previously understood. In the end, perhaps that is all that science can offer, and perhaps it is enough. The pursuit of understanding, the quest to comprehend the universe and our place in it, is itself a noble goal, worthy of our greatest efforts and our deepest commitment. James Webb has shown us how much there is yet to discover, and in so doing, it has shown us how remarkable it is that we can discover it at all. We are the universe examining itself, asking questions, seeking answers, reaching ever outward into the cosmic darkness. And in that reaching, we express something fundamental about the human spirit, the desire to understand, to explore, to grow, and to connect with the deepest truths about existence. This is our contribution to the cosmos, and it is a profound one. When we contemplate what James Webb has revealed to us, we must also consider what it means for our understanding of physical law and cosmic evolution going forward. The observations from this remarkable instrument have not simply confirmed our existing theories with greater precision. They have instead suggested that our understanding, while impressively sophisticated, remains incomplete in fundamental ways. The discovery that galaxies grew and evolved faster than our models predicted suggests that some of our assumptions about the processes governing galaxy formation and evolution may need reconsideration. Consider the implications for research into dark energy, the mysterious force that appears to be accelerating the expansion of the universe. We know that dark energy comprises roughly 70% of the universe's total energy density, yet we understand virtually nothing about its true nature. Our current model, the cosmological constant, treats dark energy as a property of space-time itself, a constant density of energy that permeates all of space. But this model may be too simplistic. What if dark energy is something more dynamic, evolving over cosmic time? What if it interacts with matter and radiation in ways we have not yet discovered? James Webb's observations, by providing an increasingly detailed map of how the universe has evolved over cosmic time, could eventually help us constrain models of dark energy and move toward a deeper understanding of this fundamental mystery. Similarly, the observations from James Webb speak to questions about the nature of inflation itself. Although inflation remains the leading cosmological theory, explaining the large-scale uniformity of the universe and the origin of its structure, it is not without critics and open questions. Some physicists have proposed alternative or modified inflationary scenarios. Others have questioned whether inflation is truly necessary or whether other mechanisms could explain the universe's properties. James Webb's observations of the early universe provide tests of inflationary predictions and could eventually lead to a more refined understanding of cosmic inflation or suggest that modifications to the theory are necessary. One area of particular interest involves what cosmologists call the running of the spectral index, a subtle feature in the distribution of matter in the universe that could be detected through careful observation of galaxy clustering patterns. If inflation is correct and occurred in a particular way, the running of the spectral index should have a specific value that can be predicted from theoretical models. James Webb and other observatories are working to measure this quantity with increasing precision. If observations show a running of the spectral index that differs significantly from theoretical predictions, this would represent a challenge to our current understanding of inflation and would necessitate rethinking some of our deepest assumptions about the early universe. The observations from James would also raise interesting questions about the nature of the first stars and galaxies and their role in shaping the universe's subsequent evolution. We have long known that the early universe was very hot and dominated by radiation, but the specifics of how the first structures formed and how they seeded the formation of larger structures remain subjects of active investigation. The discovery that galaxies form faster than expected suggests that the first stars and galaxies may have had a more immediate and dramatic impact on their surroundings than our models had predicted. One fascinating area of research that has been energized by James Webb's findings involves the study of cosmic dust in the early universe. Dust may seem like a minor component of the universe, a nuisance that obscures our view of distant galaxies. But in fact, dust plays a crucial role in cosmic evolution. Dust grains provide surfaces on which molecules can form, facilitating the development of complex chemistry. Dust absorbs visible light and re-emits it in the infrared, which means that astronomers studying dust can learn about the light from very distant galaxies that would otherwise be hidden. Most importantly, dust is essential for the formation of planets. Without dust to provide the seeds around which planets grow, the universe would be barren of worlds. James Webb has revealed that dust was present in the early universe in significant quantities. This means that the processes of planet formation were likely occurring far earlier in cosmic history than we had previously thought. If planets were forming alongside the first galaxies, then the possibility that life could have emerged early in cosmic history becomes somewhat more plausible. Of course, life requires more than just planets and organic chemistry. It requires the right physical and chemical conditions to be sustained for sufficient periods of time. But the presence of abundant planets in the early universe suggests that life may have had numerous opportunities to emerge at different times and places throughout cosmic history. The study of dust in the early universe also provides insights into the rate and efficiency of star formation and the processes by which galaxies transform their available gas into stars. By measuring the amount of dust in distant galaxies and comparing it to the amount of stellar light, astronomers can estimate what fraction of a galaxy's available gas has been converted into stars. This information helps constrain models of galaxy evolution and provides clues about the physical processes that regulate how quickly or slowly galaxies form stars. As we contemplate these various aspects of James Webb's contributions to our understanding of the cosmos, we might also reflect on the broader implications for humanity's future as a spacefaring species. The success of James Webb, despite its enormous technical challenges and cost, demonstrates that humanity is capable of undertaking ambitious projects that push the boundaries of what is technically possible. The instrument represents the collaborative work of thousands of engineers and scientists from multiple nations working together toward a common goal. This international cooperation in the pursuit of knowledge is itself a hopeful sign for humanity's future. If we are to face the great challenges that lie ahead, whether in the form of climate change, resource management, or other existential risks, we will need the kind of coordinated effort, long-term thinking, and commitment to understanding that the James Webb Project exemplifies. The development of the instruments and knowledge systems needed to address these challenges will require sustained investment and international cooperation. The example of James Webb suggests that such cooperation is possible, even when the challenges are immense and the timescales are long. Moreover, the perspective that James Webb provides on the cosmos may help foster the kind of long-term thinking that we need as a species. When we contemplate the age of the universe, the vast distances between stars, and the tremendous span of cosmic time, we are forced to think in terms of millions and billions of years. This perspective can help us appreciate the importance of sustainable practices and long-term planning. We are stewards of a planet that has taken billions of years to produce the conditions for life. Our actions today will reverberate into the distant future, affecting generations yet unborn. This responsibility is both awesome and humbling. There is also something deeply inspiring about the mere fact that we can see so far back into the universe. The light that James Webb collects has traveled for over 13 billion years through the expanding cosmos. In that journey, it has passed through regions of space where galaxies were being born and dying, where stars were exploding. It has been stretched by the expansion of the universe, scattered by dust and gas, and finally concentrated by the telescope's mirrors to be detected by exquisitely sensitive infrared detectors. The fact that this light can be captured and analyzed, that we can extract information about the properties of distant galaxies from this ancient light, demonstrates the remarkable ingenuity and persistence of human civilization. In many ways, the James Webb Space Telescope represents the culmination of a long journey that began when humans first looked up at the night sky and wondered about the nature of the stars. For thousands of years, we could only observe the cosmos with our naked eyes. The invention of the telescope extended our vision by orders of magnitude. The development of photography allowed us to gather light from distant objects over long periods of time. The development of spectroscopy revealed the chemical compositions and physical properties of distant objects. The launching of space telescopes freed us from the constraints of Earth's atmosphere. And now, with James Webb, we have created an instrument so sensitive and so sophisticated that we can observe nearly to the edge of the observable universe and nearly to the beginning of time. Yet even as we celebrate these achievements, we must remain humble about the limits of our knowledge. The universe is far vaster than we can fully comprehend. The timescales involved are so enormous that they strain human intuition. The physical laws that govern the cosmos remain partly mysterious, with quantum mechanics and general relativity still not fully reconciled. And perhaps most profoundly, we do not yet understand the deepest questions about existence itself, why there is something rather than nothing, why the laws of physics are as they are, whether consciousness is fundamental to the universe or merely an emergent property of certain complex systems. James Webb cannot answer these ultimate questions, nor should we expect it to. Rather, it provides us with observational data that constrains our theories and guides our investigations. It reveals problems with our current understanding that drive new theoretical work and inspire new observations. In this way, James Webb is not an end point in our quest to understand the universe, but rather a waypoint along a much longer journey. As we look forward to the future of cosmic exploration and astronomy, we can anticipate that James Webb will continue to generate discoveries for many years to come. The telescope is expected to function for at least a decade, possibly longer. During that time, it will accumulate vast quantities of data about the early universe, about star-forming regions, about the atmospheres of exoplanets, about 1,000 different aspects of the cosmos. This data represents a treasure trove of scientific discovery that will occupy researchers for decades after the telescope itself ceases to function. The full implications of James Webb's observations will likely not be apparent for many years. Science often proceeds in unexpected ways. Observations made for one purpose reveal phenomena that have implications far beyond their original context. Data that seems peripheral at first may later turn out to be crucial for solving an important problem. The history of astronomy is filled with such examples, where new observations or new perspectives on existing data led to revolutionary changes in our understanding. As we consider what James Webb has shown us and what it pretends for the future, we are reminded that the quest to understand the universe is fundamentally an expression of hope. It is the hope that reality is comprehensible, that the universe operates according to laws that humans can understand, that the pursuit of knowledge will ultimately lead to greater wisdom and understanding. In an age when there is much to be pessimistic about, when global challenges seem overwhelming and the future uncertain, the existence of projects like James Webb offers a counterweight, evidence of humanity's capacity for achievement, for cooperation, for the pursuit of truth and understanding. When James Webb looked too deep into space, what it found was not catastrophic revelation of our insignificance, but rather an invitation to deeper understanding. The galaxies it observed, the stars it detected, the chemical elements it revealed being forged in stellar furnaces, all of these speak to the fundamental unity of the cosmos and our place within it. We are not separate from the universe. We are part of it. The atoms in our bodies, the energy in our cells, the consciousness that allows us to wonder and dream, all of these are manifestations of the same physical laws that govern the distant galaxies that James Webb observes. This realization carries with it both humility and inspiration. Humility, because it reminds us of our small size in the context of the vast cosmos, but also inspiration, because it shows us that we are capable of understanding the vast cosmos, that the human mind can grasp truths about the structure and history of the universe that extend far beyond our immediate experience. In the light from distant galaxies, we see evidence of our own cosmic heritage and our deep connection to all of existence. The questions that James Webb raises, the mysteries it illuminates, the challenges it poses to our current understanding, all of these will keep astronomers and physicists occupied for many years to come. New theories will be developed. New observations will be made with James Webb and with other instruments. Gradually, our understanding of the early universe and the physical processes that govern galaxy formation and evolution will deepen and refine. But the ultimate significance of James Webb may lie not in any specific discovery, but rather in what it tells us about the human capacity for understanding and our role as conscious observers of a cosmos that is both vast and comprehensible. In the final analysis, James Webb looked too deep into space and found something shocking, not the shocking violation of known laws or the discovery of something entirely unexpected, but rather the shock of recognition. We recognized that the universe was more complex, more dynamic, more wonderful than we had previously appreciated. We recognized our own profound connection to that universe. And we recognized that despite our small size and brief existence, we are capable of reaching out into the cosmos with instruments and mathematics and reason to touch the light from the distant past. This capacity for wonder, for understanding, for reaching toward truth, this is what defines us as human and what connects us to the cosmos itself. There is a particular quality to the silence of space, a profound emptiness that exists between the stars. Yet this emptiness is not truly empty. It is filled with the faint glow of distant galaxies, with the radiation that has been traveling for billions of years, with fields of energy and matter distributed throughout the cosmos in ways we are only beginning to understand. When James Webb peers into this seeming emptiness, it discovers that every direction we look, every small patch of sky we examine, is filled with structure and complexity. The deepness we are speaking of when we say that James Webb looked too deep into space is not merely a depth of distance, but a depth of time and complexity. Think about what it means to observe at infrared wavelengths. The visible light that our eyes perceive represents only a tiny fraction of the electromagnetic spectrum. Beyond the red end of visible light lies the infrared, the radiation associated with heat. Every object in the universe that has a temperature above absolute zero emits some infrared radiation. Hot, young, massive stars emit strongly in the infrared. Dust clouds heated by stellar radiation glow in the infrared. Young, forming galaxies, filled with newborn stars and dust, shine brightly in infrared light. By observing in the infrared, James Webb sees aspects of the universe that would remain hidden to optical telescopes. It sees through dust. It sees the warm interior of nebulae where stars are being born. It detects the red-shifted light from the most distant galaxies, light that has been stretched so much by cosmic expansion that it appears in the infrared. The infrared detectors on James Webb represent the culmination of decades of technological development. They are cooled to cryogenic temperatures, where they become exquisitely sensitive to individual photons of infrared radiation. The noise that would drown out faint signals at warmer temperatures is virtually eliminated at these ultra-cold temperatures. This allows the detectors to count individual photons arriving from distant galaxies, to measure their properties with extraordinary precision. It is as if we have developed a sense organ sensitive to heat and radiation from across billions of light years. Understanding how James Webb works, and what it has revealed requires us to appreciate not just the technical accomplishments, but also the conceptual frameworks that allow us to interpret its observations. Astronomy is not merely a matter of pointing a telescope at the sky and observing what is there. It requires theories, models, and frameworks that help us understand what we are seeing. When astronomers observe a distant galaxy with James Webb, they are not simply photographing an object at a particular location. They are observing the light that was emitted billions of years ago, and they are using that light to infer properties of the galaxy when it was much younger. The combination of observations and theoretical models allows us to construct a history of cosmic evolution. The study of galaxy evolution is particularly important for understanding how the universe changed from the nearly uniform state that existed shortly after the Big Bang to the rich structure we observe today. In the early universe, the density of matter varied only by tiny amounts from place to place. Over billions of years, gravity amplified these tiny variations into enormous structures, the galaxies, galaxy clusters, and cosmic filaments that we observe. But the details of how this happened remain a matter of investigation and debate. James Webb's observations are providing new constraints on how this process unfolded. One of the key insights that has emerged from James Webb's observations is that the relationship between galaxies and their central supermassive black holes is more intimate and more important than we had previously realized. We knew that supermassive black holes exist at the centers of galaxies. We knew that when these black holes are actively accreting material, they can release tremendous amounts of energy. What James Webb has revealed is that this energy can have profound effects on the surrounding galaxy, regulating how much gas is available for star formation and potentially triggering or suppressing the birth of new stars. The black hole and the galaxy are linked in a symbiotic relationship, each influencing the development of the other. This feedback mechanism between black holes and their host galaxies is thought to be crucial for understanding why galaxies evolve as they do. In the present-day universe, we observe that most large galaxies contain a supermassive black hole at their center with a mass that is proportional to the mass of the galaxy's bulge, the concentrated core of stars at the center of the galaxy. This relationship suggests that black hole growth and galaxy growth are coupled somehow. But the details of this coupling and how it operates in different cosmic epochs remain to be fully understood. James Webb's observations of the early universe are helping to illuminate these details. The discovery that active supermassive black holes were common in the early universe was surprising to many astronomers. In the present-day universe, most large galaxies have black holes that are not actively accreting significant amounts of material. They are relatively dormant. But in the early universe, a large fraction of galaxies appear to contain actively growing supermassive black holes. This suggests that the early universe was a more violent, more energetic place than the present day, with frequent interactions between galaxies and between galaxies and intergalactic gas. As the universe aged and the density of galaxies decreased due to cosmic expansion, these interactions became less frequent, and black holes had fewer opportunities to actively grow. The implications of these findings extend throughout our understanding of cosmic history. If black holes were actively growing in most galaxies in the early universe, and if this growth releases tremendous amounts of energy, then the intergalactic medium, the space between galaxies that is filled with hot, diffuse gas, must have been heated by this energy. This heating could have suppressed the formation of new galaxies by making it difficult for gas to cool and condense to form stars. In this way, the growth of black holes may have actually slowed down the rate at which new galaxies formed, creating a kind of self-regulation in the cosmic system. We are beginning to appreciate that the universe is not a collection of independent objects, galaxies, stars, black holes, each evolving according to its own internal laws. Rather, these objects are interconnected in complex ways. The radiation from stars and black holes affects the temperature and ionization state of the surrounding gas. The movement of galaxies causes collisions and interactions that reshape them. The gravity of dark matter determines the overall structure in which all visible matter is embedded. The universe is a single, unified system, with processes and feedback mechanisms operating at every scale from the smallest stars to the largest galaxy clusters. James Webb's observations have given us a window into how this complex system operated in the early universe. But more importantly, they have raised new questions that will occupy researchers for years to come. How exactly does the energy from black holes couple to the surrounding gas? What physical processes determine the efficiency with which black holes can grow? How do the interactions between galaxies shape their evolution? These are questions that require both new observations and new theoretical developments to answer. The data from James Webb has already begun to shape the next generation of theoretical models of galaxy evolution. Astronomers and theoretical physicists are working to develop computer simulations that can reproduce the properties of the galaxies James Webb observes. These simulations incorporate our best understanding of gravity, hydrodynamics, star formation, feedback from supernovae and black holes, and many other physical processes. By comparing the results of simulations to observations, scientists can identify which physical processes are correctly understood and which require reconsideration. This iterative process of observation and theory is at the heart of scientific progress. Observations reveal discrepancies between reality and our expectations. These discrepancies motivate new theoretical work. The new theories make predictions that can be tested with new observations. Through repeated cycles of this process, our understanding gradually becomes more accurate and more complete. James Webb has accelerated this process by providing observations of the early universe with unprecedented detail and sensitivity. The technological achievements represented by James Webb also deserve recognition in their own right. The construction and operation of a space telescope is one of the most challenging engineering projects that humans have undertaken. It requires coordinating thousands of people across multiple nations and continents. It requires solving technical problems that have never been solved before. It requires maintaining quality control and reliability standards of the highest order. The fact that James Webb has succeeded in this endeavor is a testament to the capability and dedication of the engineers and scientists involved. Moreover, the successful operation of James Webb demonstrates that humanity is capable of undertaking ambitious projects that require sustained commitment over decades. The concept for James Webb was developed in the 1980s. The construction and testing spanned the 1990s and 2000s. The launch occurred in 2021, and the first observations were released in 2022. This is a project that required the sustained commitment of multiple generations of scientists and engineers. It required the political will and the funding commitment of governments across multiple nations. It required the trust that future generations would value what had been promised for decades. This kind of sustained commitment to long-term projects is increasingly rare in the modern world, where funding often focuses on short-term results and immediate payoffs. Yet James Webb demonstrates the immense value of long-term investment in fundamental science. The observations returned by the telescope are already providing insights that will influence astronomical research for decades. The technological developments spurred by James Webb's construction have applications far beyond astronomy. The international cooperation required to build and operate the telescope serves as a model for how nations can work together on projects of mutual benefit. Looking forward, the success of James Webb will likely inspire the development of even more ambitious astronomical instruments. Plans are already underway for the next generation of space telescopes, including a potential successor to James Webb with even greater sensitivity and wavelength coverage. There are also plans for extremely large ground-based telescopes that will complement space-based observations. With each new instrument, we gain new windows into the cosmos and new opportunities to deepen our understanding. Yet we must also recognize that our understanding of the cosmos, while impressive, remains incomplete and imperfect. We do not know what dark matter is. We do not understand the nature of dark energy. We have not reconciled quantum mechanics with general relativity. We have not detected any signals from technological civilizations elsewhere in the universe. We do not fully understand the origin of life or the conditions that allow life to emerge and flourish. These are great mysteries that continue to challenge and motivate scientists to push the boundaries of knowledge. James Webb's observations, while spectacular and revealing, represent just another step in humanity's long journey toward understanding the cosmos. They raise more questions than they answer. They challenge our existing theories and force us to reconsider our assumptions. They inspire new investigations and new lines of inquiry. And ultimately, they remind us of the profound fact that the universe is stranger and more wonderful than we can fully comprehend, yet comprehensible enough that human minds can grasp its basic structure and history. This is the shock that James Webb found when it looked too deep into space, not the shock of incomprehensible mystery, but the shock of surprising comprehensibility. We have found that our understanding was incomplete, that the universe was more complex than we realized. But we have also found that by looking deeper, by developing better instruments, by working collaboratively across national and professional boundaries, we can continue to expand our understanding. The cosmos invites us to explore it, to question it, to seek to understand it. And through this process of exploration and understanding, we express something fundamental about the human spirit, our capacity for wonder, for creativity, for the pursuit of truth. In this sense, James Webb is not merely an astronomical instrument. It is a symbol of humanity's place in the cosmos as a species capable of understanding itself and the universe in which it dwells. In the final moments of reflecting on what James Webb has shown us, we must return to the simplicity and elegance of the fundamental insight that observation provides. The human eye evolved over millions of years to detect visible light in the narrow range of wavelengths that pass through our atmosphere and reflect from terrestrial objects, is suddenly extended far beyond its natural capabilities. We can now see in infrared, detecting the heat radiation from distant objects. We can measure the spectrum of light, determining the chemical composition of galaxies billions of light years away. We can observe how the universe changes as we look back in time. These capabilities, which would have seemed impossible just decades ago, are now routine. James Webb stands as a monument to this human capacity for extending our senses and our understanding beyond the limitations of our biology. It is a monument to creativity, to determination, to the collaborative effort of thousands of people working toward a common goal. It is a monument to our curiosity about the cosmos and our desire to understand our place within it. And most profoundly, it is a monument to the power of human reason and the accessibility of truth through careful observation and rigorous thinking. When we contemplate the observations from James Webb and their implications, we are contemplating not just the nature of the universe, but the nature of ourselves, as observers, as thinkers, as inhabitants of this cosmos. We are contemplating what it means to be conscious beings in a universe that is 13 billion years old and billions of light years across. We are contemplating the apparent miracle that our minds, evolved for survival on a small planet, are capable of understanding the large-scale structure of the universe and its history. Perhaps this is the true shock that James Webb found when it looked too deep into space. Not the shock of finding something unexpected about galaxies, or black holes, or star formation, but the shock of finding, in the observations of an ancient cosmos, confirmation of our capacity to understand it. The shock of realizing that consciousness, intellect, and curiosity are not marginal to the universe, but fundamental expressions of the same physical processes that govern everything else. The shock of recognizing that we are not strangers in an alien cosmos, but expressions of the cosmos itself, windows through which it perceives and understands itself. This realization should inspire both humility and hope. Humility, because it reminds us that our place in the universe is small and our time is brief. The universe was ancient long before we emerged, and it will persist for eons after our species and our planet have faded into insignificance. The light from the galaxies that James Webb observes left on its journey billions of years before the Earth existed. In the cosmic perspective, the entire span of human history, all of our achievements, all of our struggles, all of our works, would be imperceptible to any observer viewing the universe as James Webb shows it to us. Yet there is also hope in this realization. Hope that through the exercise of reason and the pursuit of knowledge, we can extend our understanding beyond the limitations of our immediate experience. Hope that the universe, for all its vastness and age, is comprehensible to beings fashioned from its own substance. Hope that consciousness and intelligence are not cosmic flukes, but manifestations of deep principles embedded in the nature of the universe itself. Hope that if we continue to ask questions, to observe carefully, to think rigorously, we can continue to deepen our understanding and move toward greater wisdom. The journey of understanding the cosmos is one of the great adventures of the human spirit. It has taken us from a time when the earth was thought to be the center of all creation, to a time when we understand ourselves as inhabitants of a small planet orbiting an ordinary star in one of billions of galaxies. It has taken us from observing with our naked eyes to peering through telescopes and electronic instruments that extend our vision into wavelengths invisible to human sight. It has taken us from simple questions about the nature of stars to profound questions about the origin and structure of the universe itself. James Webb represents another milestone in this long journey. It shows us the early universe in unprecedented detail. It reveals that the universe was more complex, more dynamic, and more wonderful than we had imagined. It shows us the first galaxies, the ignition of the first black holes, the rapid production of the chemical elements that would eventually lead to planets and life. And in doing so, it invites us to ask deeper questions about the nature of cosmic evolution and our place within it. As we stand at this moment in cosmic and human history, with the observations from James Webb fresh in our minds, we can contemplate with awe the universe that the telescope has revealed. We can marvel at the fact that photons that began their journey over 13 billion years ago, that have traveled across the expanding universe, past countless stars and galaxies, have finally reached our instruments and been translated into images and data that our minds can comprehend. We can reflect on the meaning of the fact that we are capable of this, that consciousness and reason have arisen in the universe and can reach back to understand the universe's own history. The questions that James Webb raises will occupy the scientific community for decades. How did the first galaxies form so quickly? How did supermassive black holes grow to such enormous sizes? What role did black holes play in shaping the evolution of galaxies? How has the star formation rate evolved over cosmic time? What can we learn about inflation from observations of the galaxy distribution? These questions and hundreds of others will drive new research, new observations, new theoretical developments. Yet beyond the specific scientific questions, there is a broader philosophical question that James Webb's observations raise. It is the question of what the universe is and what our place is in it. For millennia, humans have looked up at the sky and wondered about these questions. We have developed mythologies, philosophies, and religions to answer them. In the past few centuries, we have developed science as a method for pursuing the truth about the universe. And with instruments like James Webb, we have achieved unprecedented success in understanding the universe as it actually is, stripped of mythology and speculation. The result is a cosmos far stranger and more wonderful than we could have imagined. It is a cosmos that had a beginning, that has evolved over billions of years, that is populated with billions upon billions of galaxies, each containing billions of stars. It is a cosmos where the laws of physics are universal, applying equally to the motion of planets and the evolution of galaxies. It is a cosmos that is produced, on at least one small planet orbiting an ordinary star, the conditions necessary for life to emerge. And that life has evolved the capacity to understand the cosmos itself. This is a remarkable story. It is a story of emergence and complexity, of order arising from chaos, of consciousness arising from matter. It is a story that connects us intimately to the cosmos, and to the billions of years of cosmic history that preceded our existence. We are made of the atoms that were forged in stellar furnaces. We are animated by the same physical laws that govern the universe. We are the universe understanding itself. In the end, James Webb looked too deep into space and found something shocking: ourselves. Not in the form of other beings looking back, but in the form of our capacity to understand what we are looking at. We found that we can comprehend the cosmos, that we can reach across billions of light years and billions of years of time and grasp the nature of distant galaxies and ancient epochs. We found that consciousness is not a marginal phenomenon in the universe, but a central expression of the universe's nature. We found ourselves as participants in the cosmic story, as observers capable of understanding what we observe. This realization should inspire in us a sense of profound responsibility. If we are the universe aware of itself, then the choices we make matter not just to us, but to the universe in some sense. The way we treat our planet, the way we develop our knowledge in technology, the way we relate to each other and to the living world, all of these are expressions of our role as conscious beings in a conscious cosmos. The light from ancient galaxies that James Webb observes has traveled across billions of years to reach us. This is not an accident. It is an invitation and a challenge. An invitation to deepen our understanding and a challenge to live up to our role as bearers of consciousness in this remarkable universe. As we continue to analyze the data from James Webb, as we develop new theories to explain its observations, as we plan the next generation of observatories, we do so as participants in a grand human endeavor, the pursuit of understanding. This endeavor connects us to all those who have come before us and looked up at the sky with wonder. It connects us to the countless scientists and engineers who built James Webb. And it connects us to future generations who will build upon our knowledge and understanding. In this sense, the pursuit of understanding is not just an intellectual exercise. It is a profound expression of what it means to be human. It is our way of participating in the cosmos and contributing to its self-awareness. The shock that James Webb found when it looked too deep into space, in the final analysis, is the shock of wonder at a universe that is both vast and comprehensible, both ancient and still evolving, both fundamentally mysterious and increasingly transparent to our understanding. It is a shock that motivates us to ask deeper questions, to observe more carefully, to think more rigorously. It is a shock that reminds us of how much we have learned and how much more there is to learn. And it is a shock that affirms our faith in the power of human reason and the value of the pursuit of truth about the cosmos and our place within it. This is the legacy of James Webb and the legacy of science itself, a continuous reaching toward greater understanding, an unending quest to comprehend the universe and ourselves. There is a quality to deep observation that transcends mere data collection. When we look deeply into the cosmos, when we gather ancient light and analyze it with our instruments and minds, we are engaging in something that touches the deepest aspects of human experience. We are seeking meaning. We are seeking connection. We are seeking to understand not just what the universe is, but why it exists and what role we play in it. These are not questions that science can answer in the traditional sense, with equations and predictions. But they are questions that science can inform and illuminate. James Webb has given us new data to contemplate as we ask these ancient questions. The data shows us a universe that is more complex and more wondrous than we had previously appreciated. It shows us that the processes of cosmic evolution were occurring more rapidly than we had calculated. It shows us that the first galaxies and the first black holes were already established when the universe was less than 1 billion years old. It shows us that the raw materials for the emergence of complex chemistry and ultimately life were being produced abundantly in the early universe. All of these observations deepen the mystery of existence even as they illuminate it. In the end, perhaps the most profound realization that James Webb offers is not about the galaxies it has observed or the black holes it has detected, but about ourselves, about what it means to be conscious beings capable of understanding the cosmos. The light that James Webb collects represents a direct connection between our minds and the distant universe. When we observe that light and extract information from it, we are engaged in an act of understanding that reaches across billions of years of cosmic time. This act of understanding is itself a remarkable fact, worthy of contemplation and wonder. We are stardust that has become conscious. We are the cosmos examining itself. We are expressions of the same physical laws that govern galaxies and black holes. And through instruments like James Webb, we have the capability to examine the cosmos and learn its secrets. This is not a coincidence or an accident. It is a fundamental feature of the universe, that matter, when organized in certain ways, becomes aware. And when it becomes aware, it can direct its awareness outward to comprehend the larger structures and patterns that gave rise to it. The observations from James Webb, in looking too deep into space, have found this fundamental fact about the universe and about ourselves. They have found that consciousness is not a marginal phenomenon, not an accident of evolution on a small planet, but a central feature of the universe's nature. When photons from ancient galaxies trigger detectors in James Webb's instruments, when those signals are translated into images and data, when human minds contemplate and analyze that data, in all of this, the universe is becoming aware of itself. This is the true shock that James Webb found when it looked too deep into space. It is a shock that should inspire in us a sense of awe, responsibility, and hope. A sense of awe at the fact of our existence and our capacity to understand. A sense of responsibility for what we do with that capacity. And a sense of hope that through continued pursuit of knowledge and understanding, we will learn to live more wisely, more compassionately, and more sustainably on this small planet in this vast cosmos. As we conclude this journey through the implications of James Webb's observations, we return once more to the fundamental question that has driven astronomy since the beginning of human civilization. What are we? What is our place in this cosmos? These questions seem simple, yet they contain profound depths that philosophers and scientists have grappled with for millennia. The answer that James Webb provides is both humbling and exalting. We are small. Our planet is a tiny speck in a cosmos of billions of galaxies. Our species is young. The universe was billions of years old before we emerged. Our individual lives are brief moments in the vast span of cosmic time. And yet, we possess the remarkable capacity to understand the cosmos that created us. We can observe light that has traveled for billions of years. We can analyze that light and extract information from it. We can develop theories that explain the observations. We can ask questions and seek answers. This capacity for understanding, this consciousness that allows us to contemplate our own existence and the existence of the universe, is itself a manifestation of the cosmos's nature. When we look at the images from James Webb, we are looking at ourselves in a profound sense. We are looking at the universe as it was billions of years ago, before our galaxy formed, before our sun ignited, before our planet coalesced from cosmic dust. And in looking at this ancient universe, we are understanding the history that led to our existence. We are tracing the cosmic lineage that connects us to the most distant galaxies and the earliest moments after the Big Bang. We are realizing that separation between observer and observed is not as absolute as it might seem. We are part of the universe that we observe. When we understand the universe, we are understanding ourselves. When we contemplate the cosmos, we are contemplating our own nature and origins. This realization transforms how we think about the significance of astronomical observations. They are not merely collections of data about distant objects. They are expressions of the universe's capacity to know itself through the consciousness of beings that have emerged within it. They are testimonies to the remarkable fact that consciousness has arisen in the cosmos, and that this consciousness can understand the larger structures and processes that gave rise to it. In this sense, every observation, every discovery, every expansion of our understanding represents an expansion of the universe's self-awareness. The work that James Webb is doing, and the work that will be done with its data for years to come, is therefore not separate from the larger questions about meaning, purpose, and value. It is intimately connected to them. When we pursue understanding, when we ask questions about how the universe works, we are expressing something fundamental about our nature as conscious beings. We are exercising the capacity that makes us human. Our curiosity, our desire to understand, our ability to wonder at the magnificence of existence. As we stand at this moment in history, having glimpsed the early universe through James Webb's unprecedented observations, we can look forward with anticipation to the future of astronomy and our understanding of the cosmos. There will be new discoveries. There will be new questions raised. There will be new challenges to our existing theories. And through all of this, the human endeavor to understand will continue. The torch of inquiry that has been passed down through countless generations of scientists and philosophers will continue to burn brightly. And future generations will add their own insights and discoveries to the growing body of human knowledge about the cosmos and our place within it. This is the legacy that James Webb has contributed to, the eternal human quest to understand ourselves and the universe in which we live.